For today's lesson, we're in Chapter 15, Section 7, talking about combinations. Yesterday we talked about permutations, and today we're going to contrast that and compare that with combinations. Before we do, let's talk about subsets and sets, and remember a few things about that first. We say that set B is a subset of set A if each member of set B is also a member of set A. The empty set, which sometimes we write the word null set, or we use the symbol or the set signs with nothing in it, is the empty set. The empty set is considered a subset of any set, and the entire set is considered to be a subset of itself. Now we're reviewing that, so let's find a few subsets here, and then we'll link how that ties into the idea of combinations. So let's start out with a set containing three elements, P, Q, and R. Let's find all the possible subsets. If we list them all, here's the complete list. We're going to have the set itself, P, Q, and R. Then we're going to look for all the lists of subsets that contain two elements. So we would have P and Q, we can have P and R, and we can have Q and R. If we take the subsets that contain one element, we would have the set P, the set Q, the set R, and then of course the empty set is a subset of any set as well. Finding all the two-letter subsets, well, we've already found them, so let's just write them down separately. We've got the set PQ, set PR, set QR. Now subsets are known as combinations of the letters P, Q, and R. So yesterday, when we were doing permutations, our keywords were order and arrange. Today, for combinations, we're looking for these keywords: subset, choose, or select. Now yesterday, permutations involved really two steps. We chose something, we selected something, and then we arranged them. Today, the combinations is a simpler task. We are just choosing or selecting, and then we don't care about the order that they appear in. So let's look at our formula for this one. If we have the number of combinations of a set, the set contains n objects. We're not using all of those objects. We're using R, which is smaller than the original list. Here's one notation to write it, n choose R. Here's the other notation for combinations for n choosing R. And our formula is n factorial over R factorial times n minus R factorial. So let's put that application and that formula to good use. Let's try an example. We're going to take the word solve, which contains 5 letters, and we're going to do two parts to this problem. Let's find the combinations if we use all 5 of them, and then let's find how many combinations if we only use 2 of them. And in this case, let's put our formula to work. We're not going to write the list of all of these to save time. We'll just go ahead and do our calculations. So 5 choose 5 is going to be 5 factorial divided by 5 factorial times 5 minus 5 factorial. When we simplify that, 5 minus 5, of course, is 0. Now, 5 factorial divided by 5 factorial is, of course, 1. And what we may not remember, but what I would like to remind you, is that the 0 factorial is defined as 1 also. So all of that divides out to 1. Now, if we do common sense, how many ways are there to choose or select 5 items from a list of 5? Well, there's only one way. You choose or select all 5 of the items. So in this particular case, common sense can help verify that we have our correct answer. Here's the possibilities, though. For part 2, let's take and list 2 at a time. Now for 2A, we did list. There's 5 choices. We just take all 5. There's only one way to do that. All the combinations of taking the letters SOLVE, listing subsets of 2, we've done that for you briefly, but let's verify that that number of subsets is correct. We've got S with the O, S with L, S with V, S with E, O with L, O with V, O with E, L with V, L with E, and V with E. So let's check to see if that's correct amounts, if we missed any. Let's choose 5 choose 2. So we're looking for our NCR button on our calculator if you have it, or let's use the formula here. So the combinations of 5 elements to choose from, and we're selecting or choosing 2 of them. That's 5 factorial divided by 2 factorial times 5 minus 2 factorial. 5 minus 2 factorial simplifies to 3 factorial. 5 factorial is 5 times 4 times 3 factorial. 2 factorial is 2 times 1. And I'm going to leave 3 factorial the same because there's a 3 factorial in the numerator, and those two will divide out to 1. 4 and 2 will reduce, and I'm left with 5 times 2, or there are 10 combinations. And as we check, we've got 2, 4, 6, 8. We found all 10 of our combinations of taking the letters SOLVE, those 5 choices, and selecting 2 of them at any given time. Well, let's choose some committees. See how we can work on this. For this particular committee, what we need is we are going to select some students. We're going to select some teachers. And we're going to do this problem in 2 different ways. We want a committee of 6 members, and we want to select them from 5 teachers and 4 students. And the first way we're going to solve this is if all people are equally eligible. And the second way we're going to look at this is what if we want a committee to be representative, having 3 teachers and having 3 students, so that we've got an even amount of teachers and students in our committee. So if we take choice A here, we've got 9 people in all, and we're going to choose 6. So that's fairly straightforward. 9 choose 6, or our NCR button, our combination button on our calculator. Our formula is 9 factorial divided by 6 factorial times the quantity 9 minus 6 factorial. 9 minus 6 factorial is 3 factorial. 9 factorial in the numerator is 9 times 8 times 7 times 6 factorial. I've got a 6 factorial in the denominator, so I will stop there because they'll divide out to 1. 3 factorial is 3 times 2 times 1. Do our simplifying. The 6 factorials divide out. 9 divided by 3 is 3. 8 divided by 2 is 4. And in this particular case, we have 3 times 4 times 7, or 84 possible ways of choosing 6 people for the committee from the 9 that were eligible. The second part of the problem is a little different. It's a compound event. So if we look back at chapter 15, section 5, and we look at the fundamental counting principle, for compound events, what we need to do is we need to find the outcome for each event and then multiply the results together. Okay, so we'll find the number for each, multiply the results together. So here's where we've got our numbers in our formula from. We've got 5 teachers to choose from, and we're going to choose 3. And we have 4 students to choose from, and we're going to select 3. Okay, we started with 5 teachers, 4 students. So for teachers, 5 choose 3. For students, 4 choose 3. We're going to do each formula and then multiply the results together. So 5 choose 3 is 5 factorial divided by 3 factorial times 5 minus 3 factorial. 4 combinations selecting 3 is 4 factorial over 3 factorial times 4 minus 3 factorial. Let's simplify that. 5 minus 3 factorial is 2 factorial. 4 minus 3 factorial is 1 factorial. Let's continue to simplify. This 5 factorial, I'm going to stop at 3 factorial because there's a 3 factorial in the denominator. So 5 times 4 times 3 factorial. This 2 factorial is 2 times 1. This 4 factorial in the numerator, I'm going to stop at 3 factorial because we have 4 times 3 factorial. There's a 3 factorial in the denominator we'll leave, and then the 1 factorial, which is just defined to be 1. So let's simplify. The 3 factorials reduce to 1. 4 divided by 2 is 2. 3 factorials reduce to 1. So 5 times 2 is 10. 4 times 1 divided by 1 is 4. And the compound event, so there were 10 ways to choose 3 teachers from 5. And there were 4 ways to choose 3 students from 4. So for my compound event, 10 times 4 gives me my answer of 40. All right, let's look at a game of cards for our 4th example. In a standard deck of cards, we have 4 suits. We have the clubs, diamonds, hearts, and spades. Each suit contains 13 cards each. We want to know how many 5-card hands can be dealt if we include 4 cards from the same suit and then 1 card from a different suit. So what that means is there are 4 suits with 13 cards we're going to have to choose 4 from. So we've got 13 choose 4 for any one suit, but since there's 4 suits, we're going to take that 13 choose 4 and multiply that result by 4. 13 choose 4 represents any one of the suits, but since we've got to represent all 4 of the suits, multiply that by 4. So our formula is 13 factorial divided by 4 factorial times 13 minus 4 factorial. And again, 13 minus 4 factorial simplifies to 9 factorial. Let's continue to simplify in our parentheses in the numerator. Let's multiply 13 factorial is 13 times 12 times 11 times 10. We're going to stop at 9 factorial because we have a 9 factorial in the denominator. The 4 factorial from the denominator is 4 times 3 times 2 times 1. We start reducing. The 9 factorials divide out. 10 divided by 2 is 5. 4 times 3 is 12, and so that will divide out to 1 with the numerator there. Continue to simplify. We've got 13 times 11 times 5. That's 715. And don't forget, that's 13 choose 4 for one suit. We need to multiply that by 4 because there are 4 suits, and that gives us the choice of 2,860. Now we still haven't dealt with this last particular situation, as one card has to come from a different suit. So let's look at that possibility. There's 52 cards in a standard playing deck of cards, and we subtract the 13 cards from one suit. That leaves us remaining with 39 cards. With those 39 cards remaining, we need to choose one of them. So 39 choose 1 is 39 factorial over 1 factorial times 38 factorial. We'll take 39 factorial as 39 times 38 factorial and stop there, because the 38 factorials will divide out in the numerator and we're left with 39. Now again, we can reason this one out in our head. 39 cards, how many ways to choose one? There's 39. Alright, well, we look at this. Number of 5-card hands that include exactly 4 cards from any one suit we said was 2,860 up here from above. We multiply that times 39. We get 111,540. So that's the number of 5-card hands that include exactly 4 cards from any one suit, and then the one remaining from the other suit. Now, before I leave this section, I would like just to point out one thing. And I know sometimes you think about math words and relate them to words you understand in your normal everyday existence. And every day you have your locker and it has what's called a combination lock. Let me just say that the name is incorrect. The lock should be called a permutation lock. We learned yesterday that permutation means the order is important. If it was truly a combination lock, you would take whatever your 3 numbers were to open that lock, and it should not matter what order you put them in. As long as you dial those 3 numbers, your lock should open. If you try that, you realize that that is not the case. So just so you don't make that mistake and think of combinations like the lock. No, combination is choosing and selecting. Permutation is choosing and selecting first, and then secondly, ordering and arranging. And again, since you have to put your numbers in your combination lock in a certain order, that should be called a permutation lock. Well, that's it for today's lesson on combinations, and we'll make sure that you try to get your permutations and combinations all squared away. Remember, combinations is choosing and select. Permutations, the key words are order and arrange.